Uh, can you hear me well? Please reply in the chat if you can hear me well. Okay, good. Right. So yes. So we have the eighth assignment. So I was a little bit off with COVID, so we're a bit late publishing the assignment. But we have I have published the questions for the assignment, so you can already start doing them, and they are available on iDrew, and I'll show them to you. So I'm going to start sharing my screen, and you can familiarize yourself with the questions that will be on the assignment. Some of these questions might become examples, and I can add some more questions, but overall, this is pretty much it. So it's all to do with geometric optics. So ray diagrams where you need to build the reflection of the object. It's not a difficult one. So then you have some geometric optics. Most of them can be solved using diagrams. There are some questions about optical fibers, and then refraction again, lots of questions on refraction. And the most challenging questions are the lenses questions. So here they are, you can find them. Just in case you don't have a link, here it is. Here's the link where you can find. So you can already start doing the 8th assignment for physics. Maths will be published tomorrow, most likely, and physics maybe 2-3 days from now. Okay, so today I'm going to talk about some of these problems, some very similar problems, and just to recap, or maybe not to recap. So the first question. The first question. It says, consider light traveling from S to M. So this is water, this is air, and this is the eye of the observer. And light travels from S to M through point B. And you need to prove that, well, we need to prove that that if the light takes the shortest path, apologies if that was loud. We need to prove that if light takes the shortest path, then it will follow Snell's law of refraction. Basically, that sine phi 0 divided by sine phi 1 is, in fact, the refractive index. So this is how we're going to do that. So just give me a moment. Here it is. Apologies. Yeah. Okay. Right. So assuming that light takes the shortest path, we will use differentiation to find it. Okay, so first of all, we will find the path BS. So BS is h squared plus x squared, and square root, of course, using Pythagoras theorem. So h squared plus x squared. Okay, and then we need the path MB. MB is capital H squared plus L L minus x. So this is L and this is x. So we need this distance. We need this distance, which is L minus x. L minus x, h plus L minus x squared. So this is the path length. Okay. And the time. So let's consider the time it spends in the water. So time for going along BS is the distance BS divided by the speed, which is BS, the distance divided by the speed. And the speed in water, we know that the speed in water is C divided by N, the refractive index. So it's going to be N divided by C square root of h squared plus x squared. And now we need to find the time Bm. Bm is equal to the distance Bm divided by c, because the speed of light in air is c, is the same as in vacuum. Well, it's almost the same. It's very similar. Okay, just check that the recording is happening. So it's going to be 1 over c square root of h squared plus L minus x squared. Okay, so that's that. So the total time is the sum of the two times going from S to B and from B to M. Can I just ask, does everything make sense so far? Is there anyone who's lost? Okay. Okay, good to hear. So we add the times. So n divided by c square root h squared plus x squared plus 1 over c square root of h squared plus L minus x squared. Right. Now, to find the shortest time possible, we differentiate. We differentiate t with respect to x. So dt over dx, and we get something. Just a second. Sorry, I need to refresh this page because otherwise it's not doing it very well. Apologies. Okay, so we differentiate that. So that's going to be n over c, so that doesn't change. N over c is a constant. And then we have the derivative of the outside function. So that's, well, maybe it makes sense to just write it like this. X squared plus h squared to the power a half plus 1 over c. So L minus x. So we can write this as, does it make sense to open the brackets? Yeah, I'm just going to open the brackets just to make it life slightly easier in terms of differentiating. So it's going to be x squared minus 2xl plus L squared plus H squared. Okay, and everything to the power half. So differentiating that, I use the chain rule. So it's going to be a half x squared plus h squared to the power minus half, and multiplied by the derivative of the inside function. So multiplied by 2x. Next, I'm going to do plus 1 over c. Then again, the derivative of the outside function, a half x squared minus 2xl plus L squared plus H squared to the power minus a half, and multiplied by the derivative of the inside function, which is 2x minus 2l. 2x minus 2l. Right, so, and this must equal to 0. This must equal to 0, and okay. So let's get rid of stuff that we don't need. We multiply both sides by 2c to get rid of the c and 1/2. That's the first thing that I can immediately see. So it's going to be 2. Well, actually, we don't need to multiply by 2 because we already have the 2 here. So this 2 cancels with this 2, and this 2 cancels with those 2's. We do multiply by c to get rid of the c. So times by c, and we have x divided by square root of x squared plus h squared. Yep, then plus x minus l divided by square root of x squared minus 2xl plus L squared plus H squared. Okay, and that is equal to 0. Right, and this seems quite quite daunting. I mean, trying to solve this for x, but actually we don't really need to solve this for x. We just need to be very observant. Let's look at this triangle. Let's look at this triangle. We can safely say that sine phi 1 is in fact x divided by bs, which is square root of x squared plus h squared. Huh, interesting. That's exactly what this is. This is sine phi 1. And if we do this triangle, then we can write that sine phi 0 is the opposite, which is L minus x divided by square root, which is divided by bm, which is L minus X divided by square root of that. This is it, divided by BM, which is this, which is H. Okay, I'm just going to write it H squared plus minus X squared. And the only difference between this and this is that the signs are opposite, X minus L and L minus X, which can be easily changed as minus X minus L, and just expanding the brackets on the bottom just to show that they're the same. So which is X squared minus 2XL plus L squared plus H squared. So in fact, what we have is that this thing is minus sine phi 0. And somewhere we lost the n. We did lose the n. So sorry about that. N. So it's going to be n sine phi. So we have n sine phi 1 minus sine phi 0 equals 0, which is pretty much what we needed to prove. I'm just going to rearrange that to make it look like, so n sine phi 1 equals sine phi 0. So n is equal to sine phi 0 divided by sine phi 1, which is really cool if you think about it. And sine phi 0. So this is the refractive. This is Snell's law. This is Snell's law, which is which you're very familiar with. Just one more thing. So, and one consequence of that, I like to talk about this problem. So let's say you have a huge pond or a sea. So this is the shore. Okay, that's not a good shore. If you get shore, and this is water. This is water. And this is sand. This is sand. And your house is on the beach. This is your house. This is your house. And one morning you wake up and there's a person in distress in the water. So there's somebody in the water right here, and they're asking for your help. Now, you want to help them as soon as possible. You want to help them as quickly as possible. So what do? Do you run towards the water and then swim? Or do you run to the closest point and then swim? Or do you follow a straight line? Because, well, they told you that straight lines are the fastest. So, well, if you're like any other person on the world, you swim slower than you run. You can run faster than you swim. So apparently, if the speed at which you can run divided by the speed at which you can swim is n. N is the ratio. Oh no, please don't do that. I'm sorry. I'll be back in a second. Sorry about that. That didn't help. I tried that. Okay, that might work. Okay, if the ratio of the speeds at which you run and you swim is n, so you run n times faster than you swim. So as a matter of fact, the quickest way to get to help the person is if you draw this path and then you draw a normal line, and this is theta 1 and this is theta 2. So the fastest path, and you can prove that if that is if sine theta 1 divided by sine theta 2, theta 2 is n. Snell's law is also applicable to saving people, right? And okay, so that's about the Snell's law. Does everything make sense so far? If not, please let me know. Well, that's a bit cruel. Right. Right. So a desk lamp that can be considered a point source of light is placed 60 centimeters above the desk. And just one more second. The distance between the desk and the ceiling is 1.8 meters. The desk is 1.8 meters from the ceiling. This is the top of the desk, of course, when I say the top of the desk. So quite a difficult description. So we'll help ourselves by drawing the desk. So this is a desk, and there's a lamp. Okay, so it's a desk lamp. So let's say the lamp is like this, and the lamp can be considered as a point source of light. Yes. And there's a mirror placed on the desk. It doesn't really specify where the mirror is, but as a matter of fact, well, let's place the mirror in an arbitrary position. So we'll place the mirror here. This is the mirror. Mirror. First, we need to find the position of the image of the lamp, of the filament of the lamp. So how do we do that? Well, first of all, we draw two rays. Just as in any diagram, we draw two rays. One ray going like this, and it's being reflected. Now, of course, you want to do this reasonably accurately, and that sounds about right. So you need the angle of incidence and the angle of reflection. Of course, when you do this diagram, you need to measure those angles carefully. And then you draw a second ray of light. Let's use a different color for that. And it is being reflected like this. Same principle. Angle of incidence is equal to the angle of reflection. I hope you're all familiar with these terms from GCSEs, because otherwise you're going to have a tough time doing this. So, and then you continue the rays. You continue the rays until you have an intersection. So continue the ray like this, and you continue the ray like this. And this is where the position of the image is. Now you don't have to draw the rays to the middle of the to the edge of the mirror. It doesn't really matter where you put them. Any way you draw the two lines, the lines will intersect here. And this is the image S1. S1 is the image of the lamp. And if you draw a line, a vertical line, well, I'm a little bit off, but it should be exactly vertical and the same distance from the, so it's going to be 60 centimeters from the surface, and this is 60 centimeters because the lamp is 60 centimeters above the desk. All right. Is that unclear? Is that all making sense? Can I get a vote 1 to 10, please? Okay. All right. Very nice. And then, if you take a mirror and you point the sun at the mirror, you can reflect and you get a very nice, well, in Russia we call it a solar bunny, because it jumps like a bunny. So it's a solar bunny, and you can, if you have the ceiling of the room like this, which is 1.8 meters from the surface. 1.8 meters. Okay, that wasn't a very good idea. 1.8 meters like this. 1.8. So if you look in the mirror, you will see that the lamp is as if the lamp is under the desk, as if it's 60 centimeters under the desk, and it's shining through a mirror. So in fact, it will create on the ceiling. It will create a bright spot in exactly the shape of the mirror. It will be a triangular shape. You can convince yourself by drawing it in 3D. So let's say you have a source of light, which is here, source of light, and you have a mirror. Well, you have a triangular window, let's say, because it's just like a window. So the source of light is under the desk and it's shining through a triangular window. If you shine light through a triangular window, you will see that in fact it will create just an enlarged version of your triangle, like this. Yeah, so light is shining like this, and you'll see an enlarged version of the triangle. So it's going to be triangular shaped, and we just need to find the factor of enlargement. So let's have a look. What do we know? Well, we know this distance. We know that this distance is 60 centimeters. So that's 60 centimeters. So it's as if the light is coming from the bottom, 60 centimeters, and the whole thing, this is 1.8 meters plus 60 centimeters. That's going to be 2.4 meters. So the whole thing, the whole length is 2.4 meters. 2.4 meters. So the scale factor of enlargement, scale factor, scale factor, scale factor is 2.4 divided by 0.6, 2.4 divided by 0.6, which is what, 4? Is it though? Just a second. Oh, I see. The lamp is 1.8 meters. Okay, sorry. The lamp is 1.8 meters, not the not the table. Sorry about that. That was wrong with the question. Yeah, so the lamp is 1.8 meters, and the lamp is 1.8 meters from the ceiling. Okay, so then the this distance is not 2.4 meters, but it's 3 meters. 3 meters. 3 meters. That makes more sense. So the source of light, is 3 meters from the ceiling. Source of light is 3 meters because it's 1.8 meters plus 1.2 meters. So this is 3 meters. Okay, 3 meters. All right, so the scale factor is 3 divided by 0.6, which is 5. 3 divided by 0.6, which is 5. So the triangle would be 5 times bigger. So answer. So for A, it is 60 centimeters. So 1.2 meters. What was directly below the lamp. And B, it's So if the mirror was 5 centimeters by 6 centimeters by 7 centimeters, so it's going to be 25 centimeters, 25 centimeters, 30 centimeters, and 30, 35 centimeters, 35 centimeters. Okay, so that's that. Right. So problem 3. When looking down into a swimming pool, the pool seems shallower than it actually is. Find the actual depth if the pool is if the perceived depth is 2 meters. So I don't know if you've noticed, but whenever you look into a swimming pool, it seems like it's shallower than it is, and if you jump into it, you'll hit your feet. Whereas in fact it's much deeper than it looks. And this is to do with the refraction. This is to do with the fact that the speed of light changes. So let's consider a swimming pool and swimming pool with water. Okay. Just move it somewhere here because I'll need a diagram. Right. So this is all about ray diagrams, and just let's fill it with water. Let's fill it with water. And let's say that this is the bottom of the pool. We can consider the bottom of the pool as a source of light, S. The bottom of the pool, because we see the pool because it's reflecting light. So we can say that it's a source of light. And we're standing directly above it, so we can safely draw a light ray going straight up into our eyes. That doesn't really give us any information because this is our eye, and we can't really tell why the bottom is in a different position. So we have to draw another ray. So draw another ray of light, and which goes at an angle. Goes at an angle. And this ray would be refracted like this. So let's call this H, the actual depth of the swimming pool. And can somebody help me? Where is the perceived depth of the swimming pool? You can use annotations on the screen. Where do we see the bottom of the swimming pool? Where do we think the bottom is? S is where it actually is. S is actually where the bottom of the swimming pool is. Where the, yeah, yes, Edward, it is correct. Where the rays meet. So that's at this point. This point. So S is where the light is actually coming from S1 is the perceived position of the bottom of the swimming pool. So it's the where our brain thinks the light is coming from. And we can't blame our brain because if we know anything, our brain has been taught that light travels in straight lines. We are not told that light can travel in curved lines or bendy lines. We know that light travels in straight lines. So we see a ray of light coming from somewhere, and we continue the ray, and we think, oh, that's where it's coming from. This is called the image. We can say it's the image of the bottom of the swimming pool. Okay, so the light is coming from there. That's what our brain tells us. That's why it seems shallower than it actually is. And what we need to do now is just do some geometry. There's hardly any physics involved here, purely maths. So we'll call this theta 1, theta 2, and so this is theta 1 as well. Okay, sorry, I don't want theta 1 and theta 2. I'll just do alpha and beta. Beta, and this is alpha as well. This is beta, and this is the actual depth, and this is the perceived depth. This is the perceived depth of the swimming pool. Right, so we'll take this to be x, this distance to be x. So sine alpha is equal to x divided by h small. Yeah, this is h small, this is x. So sine alpha is opposite divided by adjacent. And sine beta is equal to x divided by h big. Yes, you are correct. You are correct. And it is tan. Okay. Yeah, we'll need to use small angle approximations here. Thank you. Tan alpha is equal to x over h small, and tan beta is x over h capital. So the thing is, because we're looking directly down, that means alpha and beta are small angles. Alpha and beta are small angles. Right. And if alpha and beta are small angles, and we're looking directly, because directly down, we can safely say that this is approximately sine alpha, because sine alpha is equal to tan alpha for small angles, and this is sine beta. No. Are there any problems with this? So does everyone know that sine alpha is approximately tan alpha when the alpha is small? Yeah? No questions here? Good. And if we express x, so x is h sine alpha, and from the other equation, x is h sine beta, and we equate them, so h sine alpha equals h sine beta, and sine alpha sine, so h divided by h small is sine alpha divided by sine beta. But sine alpha divided by sine beta is the refractive index of water. So the actual depth divided by perceived depth is n, is the refractive index of water, and we know that the refractive index of water is 1.33. So the actual depth is equal to h multiplied by n, which is 1.33 times the h times 2 times 2, and the answer is 2.66 meters. I hope I haven't made a mistake here. So 2.66 meters. So yes, the swimming pool is 33% deeper than it looks like. So any swimming pool looks is no is 33% deeper than it looks like. For small angles. Yeah, for small, because for it only works for small angles. Small, if you when look directly down, when you look directly down. So also you can look at it this way. So light travels from S to no, it's fine. I'll just show you a picture where this is not true. So swimming pool, not near me. Images. Yeah, so you can. No, it's not what I want. I just want a picture. Pre-image. And so you can see at here the swimming pool looks quite deep, quite deep, but definitely not as deep as it actually is. But at the edges, because at the edges it looks very, very shallow. So it looks as if it's getting shallower towards the end of the swimming pool. And the reason is that because the angle is no longer small. It's not a small angle anymore, and the lower this this formula stops working. So this formula only works when you look directly down the swimming pool. All right, so I hope that that was useful. I mean, drawing ray diagrams here. You'll need to draw a lot of ray diagrams for this assignment. And right, find the original path of the ray AB before being refracted by the lens. So you can see here on the picture, you see a thin lens, and you see a ray of light KLM. So KLM is refracted like this. And you need to find the original path of AB. So where is AB actually coming from? Okay, so let's see what we can do here. Okay, just a second. Right. And just a few things that I want to remind you of in lenses. So if you have a converging lens, so principal rays, so this is called the principal axis of the lens. If a converging lens is drawn like this is a converging lens. A diverging lens has the arrows the opposite way. So I'm just going to copy that. All right, so diverging lens looks like this. Okay, so this is a diverging lens. Diverging lens. And this is a converging lens. Converging lens. Converging lens. Now, if we have lenses always have two focal points and two focal planes. So if this is a focal point F1, on the same distance on the opposite side, there's a second focal point, and this plane is called a focal plane. Focal. Technology is not working as it should today. Oh no. Here we go. Here we go. So any lens has two focal points and 3, 6, 3, 6, F1, F2, and two focal planes. If you draw that, it's a focal plane. Focal plane. And this is a focal plane as well. Focal plane. And so this is a converging lens. Converging lens. And this is a diverging lens. Diverging lens. Diverging lens. It also has a focal point. It has two focal points, the converging and the diverging lens. They're quite similar in that way. So that's F1, F2, and it also has two focal planes. So they're very similar. The difference is that they bend the light different ways. So if you have an object here, an object is usually drawn with an arrow. Sorry, sorry if you know this all. Yeah, so there are three principal rays going from the object. So first of all, this distance is called u. This is the distance from the object to the lens. This is the object distance. And this is the object, and if you draw a ray, first ray, a ray always goes through the center of the lens without being refracted. So this is the first principal ray. Okay. The second principal ray goes parallel to the optical axis, the main optical axis, and then goes through the focal point. And the point where they meet is the position of the image. So this is the image. And there's another ray going down through the focal point, through the first focal point, and then exiting parallel to the optical axis. Okay, so going to the first focal point and then parallel, straight through. This is the second principal ray, the third principal ray. Then the numbers are arbitrary. I mean, you can call them the other way around. Doesn't really matter. So the principal rays, principal rays. Right. So if you have a diverging lens, it's slightly different. So you have if you have a diverging lens. So this is the object. So there are three rays as well. So the first ray goes parallel. Well, okay, the first ray, let's keep it the same. First ray goes through the center of the lens unrefracted, always through the center of the lens unrefracted, and that's the first principal ray. The second principal ray goes parallel, and then it doesn't bend this way, it bends the other way. So it bends as if it's coming from the focal point. So it goes from here, and I'm just going to delete that. The focal point, and it looks as if it's coming from here. Okay, and the third, is there a third though? As if it's coming from the focal point. No, it's it's coming from then comes out parallel. Oh yes, so the third ray looks as if it's coming towards the second focal point. This is a tricky one. I don't normally draw it. If I'm doing a diagram, I don't draw it. I just say, okay, so it goes like this, and then it comes out like this. It's towards the second focal point and comes out parallel, which can be useful sometimes, but it's just an overkill. So that's the first, that's the second, and that's the third principal ray. So we can delete that and just draw over it using dashed lines. Okay, so hopefully that makes sense. There's also a thing called magnification, which is the size of the object divided by the size of the image. So the height of the object, height of the image, and magnification is height of the image divided by height of the object. This is magnification. Okay. Right. And hope that makes sense. Now, in here, the image is at this point. This is the position of the image. And you can see that the image is diminished. It's so it's smaller. So image is virtual because light doesn't actually cross at this point. It's virtual. It's diminished, and that's that. Okay, so I hope I didn't. I hope that wasn't too boring for you. I hope at least you've learned one new thing. Uh, yeah, just tell me if type one if you learned anything new from these two diagrams, and type 0 if you didn't learn anything new. Just so I understand. If you did learn something new, type 1. Oh, that's good. So not in vain. That's good to know. And okay, so here we have an arbitrary diagram. We don't know where the focal point is. What if you place the object before the focal point? Well, for the diverging lens, it doesn't really make any difference. It will be just the image in a slightly different position. For this one, it's going to make a difference. So the image is going to be virtual. Yeah, it's just going to be in a different position. You can look it up. There's loads of diagrams like this. So the point here, the first thing that you need to do in this example is to find the focal plane and thus find the focal point. So as long as you find the focal point, you can very easily find the path of the ray AB, because if the focal point is here, for instance, you can just draw the line and it's going to go like this, right? It's going towards the focus and out this way. So the problem is to locate that focal point. So how do we do about it? Well, just a second. Oh, I see. So we're gonna use we're gonna draw a line parallel to KL through the center of the lens. So this is KL. So we're gonna extend that. And we're gonna draw that through the center of the lens. Okay. We're using the fact that a parallel beam of light always gathers at the focal point. So we're using the fact that a parallel beam of light, parallel beam of light is always refracted such that it meets at the focal plane, not the focal point necessarily, at the focal plane. How does that work? Well, if we have a lens, if we have, I'm just going to draw a lens like this. So if you have a parallel beam of light, this is the focal point. This is the focal point, and this is the focal plane. The beam will meet somewhere here. And this is important for understanding. And it doesn't only work with a converging lens, it works the same way with a diverging lens. It's just they meet on the opposite side. So if you have a diverging lens, sorry for my drawing, and if you have a parallel beam of light hitting a diverging lens, and you have a focal point, so the focal point is here, for example, and the focal point is here. So you draw the focal plane. So this is the focal point, F1, this is F2, this is F, and the rays look as if they're coming from somewhere here, somewhere here. The rays will be coming out this way. Okay, so even with a diverging lens, the parallel beam of light meets at the focal plane. So we need to find the focal plane. So you can see that KL is parallel to this ray. That means the rays that are coming out of the lens, so these two are parallel. That means LM and this ray will be meeting at the focal point. And all we need to do is draw this. Delete that. And this is where they meet. Okay, and we know that this goes through the center of the lens unrefracted. So we've located the focal point, the focal plane, and all we need to do is just draw the focal plane, measure this distance, and draw the same distance to the other side. So what we're going to do, well, you can use you will use a compass for that. So you draw this distance, measure the same distance from the other side, and that's your focal point. That's one focal point, and that's another focal point. F2 and F1. And now all you need to do is draw a line from the focal point through A, and then just draw over it. So, bam. This is the path of the ray AB. So there are several questions like that in the assignment. Yeah, let's have a look at one of them. So this is this one. So you need to continue the ray DE. You need to continue the ray DE for an arbitrary, for a different direction. Then here you have the source and the image. You need to find where the lens is. And here you need to, what do you need to do? Determine the focal point. You need to determine the focal point of this lens. This is another thing that you need to do. Okay, so is that making sense? Is that making sense? Hopefully. How much time do we have? We have 15 minutes to go. All right. This question. Oh, uh, there is a question like that. There's a question like that here, and I'm particularly proud of my vector drawn spider. Uh, so we have an ant is crawling parallel to the principal axis of a diverging lens with a speed. Its path is offset. Find the speed of the ant's image at the moment when the ant crawls through the focal plane of the lens. So an ant is crawling towards a lens, and you see the image of that ant, and you need to find the speed of that image. So let's have a look. So okay, I'm going to cheat a little in terms of I'm going to not draw the diagram. Or actually, why not? Draw the diagram. Okay. So first of all, oh, I forgot one thing. So when we when we take when we take a lens, so this is U, and this distance is called V. This is the image distance, V. And for a converging lens, there's a um, there's an equation. So 1 over U plus 1 over V is equal to 1 over F. This is the thin lens formula for the converging lens. Right. So this is the relationship between the distance from the object to the lens and from the lens to the image. And F is the focal length, of course. And you can look up the formula for the diverging lens as well. It's very similar, just with a minus. And okay, so what's happening? A bug is crawling towards a convex lens at speed 2 centimeters per second. So a bug is crawling. Find the speed of the image when the bug is f over 2, so when it's half the focal distance away from the lens. A is 3 centimeters, and the focal length is 6 centimeters. So that's 6 centimeters, so that's 3 centimeters as well. All right. So how do we even approach that? Well, there are different ways. You can one way to do it would be to say, okay, we can, let's say the bug moves a tiny distance. The bug moves a tiny distance x, and then you find the initial position of the image and then the final position of the image, and then you then you then then you then you find it. Just a second. 0.8 divided by yes. Okay. Fair enough. So you can find the displacement of the image by construction. Okay. So you can find the image of point A and you find the image of point B, and then by construction you determine the distance traveled by the ant, and then you can find out the speed. I'm gonna use a slightly different way here. So I'm gonna write. Okay, so this is the ant. Let's find where the image is. So I'm going to draw a ray of light coming from through the center unrefracted, and we know that the light coming from the ant, like parallel, it comes off going through the focal point, through the other focal point. So we measure this distance. We draw it from here. So that's the focal point. That's the other focal point, F1. And light coming from the ant, from the bug, goes here, parallel, and then goes through the focal point. And if we continue that, that's where the image is. That's where the image of the ant is. So call it A1, A prime. So the ant, this is the image. And we move the ant slightly. We find the new position of the ant, and we find the how much it's shifted. But I'm gonna do it slightly differently. So I'm gonna say, okay, let's say that this is you. Now, I'm not gonna say that this is you because it's gonna get very confusing. I'm gonna say that this is distance of the this is distance of the object, d0, and this is the distance of the image, distance di. And I'm going to write the thin lens equation. 1 over dO plus 1 over di. I'm just using different terms. Why am I using different terms? Is because I've already have v, and v is the speed, so I don't want to use v for the distance. Okay, so is 1 over f, and I know that the d do the derivative. I'm not going to do that. I know that the derivative of do is how fast this distance changes. Is in fact v0 is the speed. Okay, speed is how fast this changes with respect to t, of course. And I'm gonna rearrange this because I need the speed of the image. The speed of the image, vi, is the derivative of the distance of the image. But that's only the horizontal speed. This is the horizontal speed of the image, not the vertical speed. Horizontal speed of the image. Because it's the change of if this is the change of the image distance, so that's only the horizontal speed. And I presume it's going to be moving vertically as well, but we'll show that in a bit. But let's focus on differentiating first. So I'm going to rewrite this. I'm going to say, okay, I need to find di from this equation. So 1 over di is equal to 1 over f minus 1 over d naught. And this is going to be d naught minus f, so t, that's f, divided by f d0. So di is going to be equal to f d naught divided by d naught minus f. Okay, it doesn't look good. It doesn't look too good, but I'm gonna differentiate that. So di prime, differentiating that, is equal to, so we use the quotient rule here. It's going to be derivative, well, f is 6, so we can safely say that this is 6 centimeters and this is 6 centimeters. We can differentiate that, so it's going to be derivative of this, so it's going to be 6 d naught prime multiplied by d naught minus 6 minus 6 d naught multiplied by d naught prime, and all over d naught minus 6 squared. Okay, and that's the horizontal speed of the image. And we know that the speed of the object, which is 2 or 0 0.2, 0. I made a mistake here. 0 0.2 centimeters per second, and the distance is 3 centimeters because it's f over 2. So it's going to be 6 multiplied by the speed, which is 0 0.2, which is, and this is d3 minus 6, minus 6 multiplied by 3 multiplied by 0 0.2. 0.2 divide all over d0 minus 6, so 3 minus 6 squared, that's 9. And as a matter of fact, this is minus 3.6, so it's minus 7.2, 7.2 divided by 9, which is 0.8 centimeters per second. But that's the horizontal speed. That's the horizontal speed of the image. Now let's draw some diagrams and see if we can find something interesting here. I'm just going to tidy this up a little. So this is 3. Okay, yeah, I'm just going to tidy it up. Okay, so this is the ant, and assume the ant has moved from this position to a slightly different position here. Very, very small. In time, in a very small time, it's moved from here to here. And let's draw. So first of all, I'm just going to draw the optical axis, the principal axis of the lens. Then I'm going to find the second focal point yet again. I just wasn't happy with the neatness of the diagram. So that, take this here, and that's the focal point. That's the focal point. Delete that. That's the focal point. F1. Now, we start drawing principal rays. So first, principal ray goes from the ant through the middle of the lens. That's the first principal ray. The second principal ray goes parallel to the axis and then goes through the focal point. So continuing these two rays, we can find the position of the image. This is the image of the ant. So if this is A, this is A prime. Now, when when it moved to B, you can see that you can very similarly draw two rays. So one going like here, going through the middle. That's the first principal ray. And the second principal ray follows exactly the first one. Follows exactly the same way because it's still going along the same straight line. So all I need to do is just to extend this, and this is the new position of B. This is B. So you can see quite a peculiar thing. The image moves along this line. The image moves along this line. The image moves along this line. And this is B prime. B prime. And if we know that horizontally it has moved this distance in time t, in a given time, given this distance, and if we were able to find this angle, alpha, then this distance is the horizontal speed, which is times time. Yes, the horizontal speed Vx multiplied by t. Then this distance is going to be the same thing, but divided by cosine alpha, because cosine alpha is this divided by that. So the total speed, the speed is the derivative of the image, or the speed of the image, divided by cosine alpha. I hope that makes sense, because so what we did here, we know that it moves along this line. If we were able to find this angle, that will really help us. It moves along this line, and we know that the horizontal component is 0.8. This is the horizontal component. So we need the total speed. Okay. I hope that makes sense. And what do we know? Well, first of all, I'm just going to use a bright green here. What do we know? Well, first of all, we know that this is 6. We know this is 6. We know that this is A. Now, we know that this is 45 degrees because we know that this is 3. We know that this is, well, this is A, which is 3. And we know that this is 3 as well. That's important. This is 3. And this is 3 as well. So this angle is 45 degrees. This is 45 degrees. And if this is 45 and this is double that, that means this line, FA, is 6. You can check my geometric reasoning later on, but I would like you to convince. So I would like you to convince yourself that this is 6. And this is a triangle. So F1, FA prime is a triangle. And if you look at this triangle, you will see that it has the same angle theta, alpha, as this one. So we can find cosine alpha. And cosine alpha, in fact, is, well, if this is 12, this is 6. So you can find this side. So that's 6 squared plus 12 squared, so 36 plus, so 144 plus 36, which is 160. No, 100 and, okay. Anyways, you can find, okay, you will see laziness of the 70th level. So I'm gonna find tan alpha first. Tan alpha. I know it's incredibly easy to find this, but I'm gonna find, because the numbers are too big. I'm too lazy to square them, so I'm gonna find tan alpha. Tan alpha is 6/12, so it's 1/2. I'm gonna square it. Tan squared alpha is equal to 1/4. Then that means that sine squared alpha divided by cos squared alpha is 1/4. So 4 sine squared alpha equals cos squared alpha. I'm doing crisscross. I need cosine, so it's 4 minus 4 cosine squared alpha equals cos squared alpha. So cos squared alpha equals, so that's 5, 4, so it's 4/5. So cos alpha is equal to 2 divided by square root of 5. Okay. Right. 2 divided by square root of 5. And that's all you need to do. So the speed is 0.8 divided by 2 divided by square root of 5, which is approximately 0.9 centimeters per second, which is quite cool. Right. Hope that makes sense, and hope that helps. Hope that helps in your with your assignment. So watch out for the release of maths. That should happen tomorrow. But previously it has happened that I've promised you something and well, we couldn't deliver. So, but most likely tomorrow maths is coming out. But for now, I invite you to go through these questions and do them. The numbering of the problems might change, but the problems won't. Okay. All right. So, right. It was great. It was great seeing you, and yeah. See you next week then. So do I stop sharing? Okay.
Just a quick question. Why was just the last bit question? Why was the distance 6 centimeters?
Which distance?
Like
FA
FA. Yeah, FA prime.
FA prime. Well, because this is 45 degrees. And this is 6, and this is 6. So this is 6, so this is also 6. This is 45.
Right, I can't really see your screen.
Sorry. So you see that this is if you look at this triangle, this is 3, and this is 3. And this is 45 degrees. And this is just a larger version of the same triangle. So that's 6 and that's 6.
Oh, I see. And then just the y speed derivative of I divided by cosine alpha. Surely the speed would be the Pythagoras of that triangle.
But you don't know that. You don't know this side. You don't know the vertical speed. I mean, if the image of the ant is moving like this, and we know this component, and we know the angle, we can work out the original speed. Yeah, if we know Vx, we can find V. So V is Vx.
Oh yes,
by
yes,
V
yes.
cosine
Sorry, yeah,
alpha.
yes. I see. Sorry, yeah, I see now. Yeah,
You're
thanks.
welcome. Okay. All right, see you.